Welcome to Sa Majesty Easy World Science channel. In this video, I'll be handling the shapes of molecules, or what we call the molecular geometry. To know the shapes of molecules sometimes try to give a little confusion, but I have organized a simple way for you to understand it. Remember, this is the easy world of science. I will always try to make it simpler for you. So endeavor to subscribe and share this video. Now, the three factors that I have organized that determines the shape of molecules. Most times the shapes of covalent molecules are three on the board, which are the type of hybridization involved in the central atom, then the steric number, and also the VSEPR theory. So in these three factors are not opposing. They look different, but they are the same. In the case where you couldn't understand the shape from number one, number two factor would help you, then number three will help you. Then in most cases, all of them speak the same language. So it is very quite tedious for you to memorize the shape of all the molecules in chemistry, but these are the secrets for you to get the summary of the shape of the molecule that you have not even had the name. So we go with that number one, the type of hybridization involved. The type of hybridization involved affects the shape. I'll give you the rundown of the shapes and the type of hybridization involved. If you talk about sp3 hybridized molecules, like alkane molecules, they have tetrahedral shape. Then if you talk about sp2 hybridized molecules, they usually have trigonal in shape, and that's their shape is usually trigonal. Then is when we go to the theory of VSEPR, you now know whether it's going to be trigonal, pyramidal, or trigonal planar. But sp2 hybridized molecules like the alkenes are usually trigonal in shape. Then sp hybridized molecules, most of them are commonly linear in shape. So this will also tell you the bond angles involved. So in the sp3 hybridized molecules, which is tetrahedral in shape, the bond angle should be 109.5. Then in sp2, which is trigonal in shape, the bond angle is 120 degrees, depending, it can also be 107 or less than 120, depending on the type of trigonal involved. Is it trigonal planar, or is it trigonal pyramidal, or is it trigonal bipyramidal? You will see all those when you go to the VSEPR there. So the theory will explain how and which one is involved. Then when something is sp hybridized, it's linear, and the bond angle is automatically 180. Then what if you go advanced again, because we have other hybridization form. You can watch my video on hybridization here on this channel. If you go to other forms of hybridization, like you might have sp3d hybridization, the shape of such molecule is usually trigonal bipyramidal, like in phosphorus 5 chloride, and bond angles are usually 90 and 120 degrees. Then what if it is a sp3d2 hybridized? In example is in sulfur hexafluoride. The shape of such molecule is octahedral in shape. So there are other forms of hybridization, but I've given you the 5 common ones that you might come across in your exam. So factor 1 is treated. Then factor 2 is where I'm going to write something. Steric number determines the shape, the geometry, the molecular geometry, and it rhymes with that number 1. None of them contradicts each other. Rule of factor 1 will tell you that this is this shape, and this one will tell you it is not this shape. Rather, the other ones will convince you. Steric number is actually the total number of bond pairs and lone pairs in the outermost shell of the central atom, and this determines the shape of molecules. For you to know the bond pairs and lone pairs, sum them together, you'll be able to know the steric number, and for you to know the steric number, you can predict the shape. There is established fact about the shape of a molecule and the steric number. But one should be careful here, because steric number do not just mean the total. I might have 4 as my steric number, you have 4 as your steric number, but we have different shapes. What matters is what makes up that my 4. How many lone pairs are involved in that 4? How many bond pairs are involved in my 4? If I have 4 bond pairs and 0 lone pair, I have a different shape. If you have 3 lone pairs, and if you have 3 bond pairs and 1 lone pair, total steric number is still 4. But you have a quite different shape from the one that have 0 lone pair. So it depends on the constituents of the total steric number. So we go first by identifying which one is lone pair and which one is bond pair. I'm going to use 3 molecules, which are, I'm going to use water, I'm going to use ammonia, and I'm going to use methane. From there, we will now know what we mean by bond pair, lone pair. Okay. Okay, right here we see these shapes. Let's determine their steric numbers. We start with methane. Remember, if you are determining the steric number, you will also know the designation of the lone pairs and bond pairs. So here is methane, which has how many lone pairs? 0 lone pair, but bond pair are 1, 2, 3, and 4. So there are 4 bond pairs here, meaning those electrons that were contributed is what we call contributed by different atoms. That's what makes up the bond pair. The cross here is to represent the one from hydrogen, while the dot represents the one from carbon. You can use cross for carbon and dot for hydrogen. So this is what we call the cross and dot diagram, just to know the contributions. So they are all paired. One came here, so contributed pairs are what we call the bond pairs in a covalent molecule. So the steric number here is 4. But what makes it up? 4 bond pairs and what? 0 lone pairs. Then when you come here also, we have how many bond pairs? 1, 2, 3. We have 3 bond pairs with 1 lone pair. This lone pair is the one that is not contributed. It belongs solely to the nitrogen. So this nitrogen automatically has this pair here, and it's called lone pair. It's not participating. It wasn't contributed by 2 atoms. It's only belonging to nitrogen, and is a pair. But this one here is a bond pair because 1 electron here came from nitrogen, the other came from hydrogen, and they bonded together. So this one has 3 bond pairs plus 1 lone pair, which gives us 4 as the steric number. So methane and ammonia have the same steric number, but the constituent is not the same. Methane has 4 bond pairs and 0 lone pair, while ammonia has 3 bond pairs and 1 lone pair, which will affect the shape. Then this structure here is actually water molecule, which has how many lone pairs? It has 2 lone pairs, 1, 2, plus 2 bond pairs, which is 4. So these molecules here all have 4 as their steric number. Does it mean that the steric number must be 4? No. Steric number can start from 2. Can be 3, 4, 5, 6. I'll give you examples, but I'm using this for you to understand what we mean by steric number. Now, having understood the steric number, we want to use it now to determine shape. This is a generalized fact. When the steric number of a given molecule is 4, which is made up of 4 bonds and 4 bond pairs and 0 lone pair, the shape is tetrahedral, and that is observed in sp3 hybridized molecules. So this shape, this methane, is automatically tetrahedral. Ethane is also tetrahedral because the central atom will have the steric number of 4 bond pairs and 0 lone pair. But in ammonia, we have 3 bond pairs and 1 lone pair. If this occurs, if the steric number is 4, which is composed of 3 bond pairs and 1 lone pair, the shape of that molecule is nothing but trigonal pyramidal. So trigonal pyramidal is the shape of this ammonia. This is applicable to any other molecule you will meet. If you have 3 bond pairs and 1 lone pair, the shape must be trigonal pyramidal, and the bond angle automatically is 107 degrees. But the bond angle here is 109.5 degrees. Then if you come to water, water also have 4 as the steric number, but it has 2 lone pairs and 2 bond pairs. If you see any molecule with 2 lone pairs and 2 bond pairs, the shape is V shape or bent or angular, and the bond angle for water is 104.5 degrees. So this is it for the steric number and the possible shapes. You can see the table where these facts are all listed. Okay, we can have other steric number that is not exactly 4. Let's take a look at molecules that have 2 as their steric number, like carbon 4 oxide has the steric number of 2. And then let's see what happens there. in counting steric number, double bonds are counted as 1. It's only single bonds that are counted. See what I mean? If I have such structure like this, if I want to count this, how many is the, look at the central atoms. Is it bonded to how many other atoms around? This carbon is bonded to 1, 2, 3. So the steric number of each carbon here is 3. Even this one is 3 also. So in this case, if you want to count the bonds, don't count this 1, 2, 3, 4. No, double bonds are counted as 1 because pi bonds are not counted. Even triple bond, you take it as 1 because it's only the sigma bonds that are counted. Out of these two bonds, one is sigma and one is pi. If we have 3 bonds, there will be only 1 sigma bond. So only 1 sigma bond can exist between one carbon and the other carbon. Therefore, that's why we count only 1. So the steric number here is only 3. How many lone pairs? 0 lone pair. So if you have 3 bond pairs and 0 lone pair, the shape is still trigonal, but it's going to be trigonal planar. But when we have 3 bond pairs and 1 lone pair, it becomes trigonal pyramidal. But when we have 3 bond pairs with 0 lone pair, it becomes trigonal planar. So alkenes, that's one with the double bond, like ethene should be trigonal planar in shape. You get that gist now? Boron fluoride should also be trigonal planar in shape because there is no lone pair, but rather 3 bond pairs all through. Then coming to this, what's the steric number of carbon dioxide? Is automatically 2 because the total number of atoms surrounding the central atom is 1, 2. Or you can count the bonds, which means I told you if you see double, count it as 1, 1, 2. So the steric number is 2, and there is no lone pair. So when we have 2 bond pairs with 0 lone pair, the shape is automatically linear, and the bond angle in linear shaped molecules is 180 degrees. Lest I forget, the bond angle in trigonal planar shaped molecules is 120 degrees. But in trigonal pyramidal is 107, is less than that of trigonal planar. I will explain that under the valence shell electron pair repulsion theory. Why do we have trigonal planar and trigonal pyramidal? Is the theory that will explain such possible shapes.
Wait a minute, have you heard about the majestic table? It was designed and recommended by Her Majesty himself. Here it is. The amazing thing about the majestic periodic table is that it provides a clear and colorful classification of elements from P block metals to metalloids to liquid metals. It also shows the boiling and melting points of all the elements. It also has the unique feeling of electrons in the shells of each element.
Enhance the easy learning and teaching of chemistry in schools, in universities, secondary schools, in research institutes. So this majestic periodic table, demand and a special demand, as you can see that space there highlighted, that is where you can include the name of your school, or if you are dedicating it to anybody, you can write there, because you can print it to any size you like. In a majestic size, the resolution will never be affected. So it took me about 3 months to design and provide these informations, but thank God the table is here. What made me to design this is that I discovered that these tables I see in the internet, the one I see in the market, they are not as informative as I want. And then some of them are not updated. Some still retain the fact that we have, there are like, some still see promentum has not been radioactive. Some might see them as artificial element, but it is still is a naturally occurring element, of course. So there are some modifications that this table has been made to include, and that makes it majestic.
This is super majestic.
Much love. Okay, we can take other examples. Let's see that boron fluoride. Boron fluoride will have this shape. and automatically is having 0 lone pair and 3 bond pairs. So the shape is going to be trigonal planar, and the bond angle is nothing but 120. Then can we have other molecules with more steric numbers? Yes. So if the steric number is 2 bond pairs, 0 lone pair, linear in shape. If it has 3 in total, where 2 are bond pairs and 1 lone pair, the shape is going to be angular or bent, and sometimes it can also be trigonal. Example is sulfur 4 oxide. That's SO2 is having this bent or angular shape, or some authority will tell you is trigonal if they include that lone pair. SO2 is unusual because of the fact that it will give us a shape. Remember, the sulfur is the central atom, so there will be double bond to oxygen, double bond to oxygen. Then there will still be a lone pair here, which gives this sulfur almost 10 in the shell, which is supposed not to be. So considering, if you consider the lone pair and the oxygen, you say it's trigonal planar, but in real sense it should be angular because the lone pair is not part of the structure. But it depends on the option. If you see trigonal planar without seeing bent in the shape of sulfur 4 oxide, you answer it. But if you see bent without seeing trigonal planar, you answer bent or angular. Okay? Then what if the bond pair is, we have total of 3 and then 0 lone pair? I told you earlier that that one should be exactly trigonal planar. Okay? Then if you have 4 in total, which we have 2 bond pair, lone pair like in water molecule, it is also angular like in 2 bond pairs and 1 lone pair. 2 bond pairs, 1 lone pair, 2 bond pairs, 2 bond pair tend to be angular in shape, but their bond angles are not exactly the same. Okay, then what if we have 5 bond pairs with 0 lone pair? Example is in phosphorus 5 chloride. The shape of that molecule is nothing but trigonal bipyramidal. Remember, the type of hybridization I said earlier is sp3d, and the shape is going to be trigonal bipyramidal. Then what if we have 6 as the steric number, composed of 6 bond pairs with 0 lone pair? The shape is going to be octahedral, as in sulfur hexafluoride. So it's rhyming. We are done with the steric number and the shape of the molecule. Then we go to the number 3, which is actually the VSEPR, what we call the valence share electron pair repulsion theory. This will explain to us why do we say that ammonia is trigonal pyramidal while boron fluoride is trigonal planar. We need to understand the interaction between the lone pairs and the bond pairs in the last shell of the central atom in a molecule. Okay, for you to understand this theory, we need to understand the interactions, the different possible interactions occurring in the last shell of the central atom. So here we have distances. This is distance A. We take it as A. And we have repulsion B and repulsion C. We also have repulsion D. Just watch this drawing. You have to agree with me that A is between lone pair, because this is a lone pair, this is a lone pair, and we call it lone pair repulsion. Then B is lone pair, bond pair. It appears between the distance between lone pair and bond pair, that's B. Then C is bond pair repulsion. Then D and B is the same because D and B remains lone pair, bond pair. Lone pair, bond pair, lone pair, bond pair. So we have these 3 possible interactions. So it is already an established fact that lone pair repulsion is the highest, followed by lone pair, bond pair. Then the repulsion between 2 bond pairs is small. That means anytime you have a lone pair in a molecule, it will affect the distribution of the bond pairs because of the valence share electron pair repulsion effect we are studying now. So in this theory, it is observed that lone pair repel each other more, followed by lone pair, bond pair, while the attraction is highest among bond pair, which means repulsion is least here. This explains why the shape of ammonia is trigonal pyramidal instead of trigonal planar, and this also explains why the shape of water molecule is angular or bent instead of linear that is expected theoretically from the shape. So I'll first of all explain the shape of water, which is what I have here. Water molecule is not linear as theoretically expected. The reason is because of what I have here. So drawing the Lewis structure of water, which is what we have here, but this is not the dot and line. If you want to draw the Lewis structure, you use small dots for lone pair, then use lines for bond pairs. So this structure and this structure is the same. This is oxygen. So this 4 dots shows 2 lone pairs, while this shows 2 bond pairs. So in this case, the repulsion, the lone pairs are pulling, they are pushing each other. Therefore, because they repel each other more, they will tend to bring this bond pair closer to form an angle instead of allowing them to be straight. This is not the geometry of water molecule because of the lone pair repulsion. So if they ask you why is water angular in shape instead, that's angular V shape or bent in shape instead of linear, you say because of the strong lone pair repulsion and also the lone pair bond pair repulsion. Assuming there is no lone pair and bond pair, like we only have bond pairs, water will be automatically linear. Like in carbon 4 oxide, if the steric number is just 1, 2 without any lone pair, it's going to be linear. But unfortunately, there is 2 lone pairs, so the repulsion between them is high, pushing the 2 hydrogen atoms close to form a V shape. So let's now differentiate between the so-called trigonal pyramidal and trigonal planar using the VSEPR theory. So in this case, we have boron fluoride and ammonia. Normal ammonia will have 1 pair. Then that's NH3. Then have boron fluoride or boron chloride, which will give you Cl, Cl, and Cl. So this one is trigonal planar. While this one is trigonal pyramidal. Now watch this. The steric number here is 4 and here is 3. But the difference is that 3 bond pairs are all present in each of the molecules, but there is a lone pair present in ammonia but is absent in boron chloride. Remember, boron chloride is a perfect Lewis acid because it can still accept a pair from this one that have it. So if you draw the structure, you discover that boron is still deficient of 2 electrons for it to be octet stable. Therefore, it can easily accept a pair from ammonia. So when ammonia molecule reacts with boron chloride, it forms an adduct. That is for Lewis acid-base reactions. This is Lewis base, while this is Lewis acid, because it can still accept a pair of electron from each shell. Remember, chlorine will donate 1 here. Boron has 3 in the outermost shell first, and the 3 now plus 1 electron again donated by each of the chlorine will give you 6, which makes it still require 2 to be stable. But the 2 is not here, so it's assumed that this is lone pair 0. 0 lone pair is here and 3 bond pairs are here, but it can still accept. So to explain why this is this, if you follow me and trace this, just watch. So for you to draw the shape of this, putting the atoms at the edges, this is what we got. This is like a perfect pyramid. That's why I say trigonal pyramidal. But here, if you place each atom where they're supposed to be, this is atom in the middle, boron, then the chlorine, the chlorine, the chlorine. This is not, it's just trigonal planar, a plane. It doesn't form a pyramid. Then this lone pair why won't it allow this hydrogen to be straight? So remember, this is a wrong way of representing the molecule, like if you draw it straight, because lone pair bond pair repulsion is highest. The lone pair is repelling the bond pair, pushing them to come closer, reducing the bond angle to 107, which is the bond angle here should be 120. But here it has pushed the lone pair bond pair repulsion has lessened the angle from 120 to 107. So the molecule of ammonia is trigonal pyramidal instead of trigonal planar because of the presence of the lone pair there, causing lone pair bond pair repulsion, pushing the two atoms together. So thank you for watching. If this video has helped you in any way, please subscribe and share. I cannot do without you. Much love from me to you.